is a video about nuclear fusion. I'm Sam Pickett.
And I'm Henry Leach.
Last month, the nearest star to the Earth was in California.
U.S. scientists making a huge breakthrough. A source tells CNN that for the first time ever, researchers have been able to create energy from a fusion reaction.
And that is creating more energy from fusion reactions than the energy used to start the process.
It was just tears of joy, and I actually physically started shaking and jumping up and down.
It's taking a star and putting it in a box on Earth and tapping that energy that goes forever. It's what Iron Man has in his chest.
But basically, it's a giant step towards a clean energy future without dependence on fossil fuels.
When you heard that President Biden's goal was commercial fusion power in a decade, you thought what?
I thought it was nonsense.
You just heard a lot about nuclear fusion on the news. That's because nuclear fusion is very difficult to do. And in order to achieve it, there are three principal components that you need. We've drawn it up here as a sort of fire triangle that you might see in chemistry. Starting with the fuel. Fusion is when you fuse two small atoms together to make a bigger atom. That's what you're fusing. And in order to do that, obviously you need lots of small atoms to start with, and that's the fuel. That's what keeps the fusion fire burning. Now, as well as that, you need confinement. Now, these particles will only fuse at incredibly high temperatures. We're talking hotter than the center of the sun. And that means that they want to expand and it wants to dissipate. In order to stop that from happening, keep the reaction rate as high as possible so you can get more energy out than you put in, we need to squeeze it using all sorts of methods, magnets or inertia, but we need to make sure that that reaction stays as concentrated as possible. But not only that, we need to make all the reactor components as durable as possible because this is incredibly high temperatures we're talking about, and neutrons are flying everywhere and making our components weaker and weaker and less effective. So if you can make a balance between all three of these key components, then yeah, you've got fusion. But that's not as easy as it sounds. So why was fusion in the news 3 years ago? Well, the reason for that is because for the first time in history, scientists at the National Ignition Facility ignited a nuclear fusion reaction, and that means they got more energy out, as you may have heard, than they put in. This is a huge milestone, obviously, and it all happened in this tiny little capsule the size of a poppy seed, which is pretty amazing, without doubt. I mean, if you look at the actual schematic of the energy transfers going on, the laser itself, they used a laser to power the reaction. The laser only delivered 2.05 megajoules to the target itself, and 3.15 were taken out in the form of heat and neutrons. That's an energy gain of 154%. And immediately your mind jumps to the implications of this. Harnessing this energy for the grid, free energy that we've just made from fusion for the first time, seems like almost the line between not doing fusion and doing fusion has been crossed. But actually, when you look at the energies involved, you can see that 400 megajoules were input into the reaction itself to actually turn on these lasers and to deliver this 2.05 megajoules to the target. So that's a huge amount more energy than we ever gained from fusion was put into starting this whole process. And if you look at a sort of diagram here of the scales involved, you can really see that the energy out of fusion that we got was negligible compared to the entire system. And this makes it seem sort of misleading when you see broadcasters saying stuff like, for the first time, we've gotten more energy out than we put in. I mean, that simply isn't the case when you look at the reaction as a whole. You might wonder what lasers are involved in fusion necessarily, but actually they need 192 of not just these lasers, but the largest, most powerful lasers currently in the world. And they're here, and they're about the size of a room. They're massive, and there's 192 of them all in this huge circle, pointing at this one tiny capsule, delivering huge amounts of energy stored in capacitors from the national grid. And this happens in fractions of a second. The energy transfer is monumental. And, sure, maybe we got 1 or 2 megajoules out of the reaction itself, but that's really not much when you compare it to all the lasers that were involved, obviously. And yeah, technically we achieved scientific break-even, but a commercial break-even is really the real break-even that we should be talking about here. So that's the situation with the NIF currently.
But in their defense, this has never been done before. We've now achieved ignition. This is the world's leading inertial confinement fusion plant. We just need to work out how to commercialize this. So how do we do that? Well, first of all, we need to increase the repetition rate at which the lasers squeeze each capsule. At the moment, the best we can do is a cool-down time of around 10 to 14 hours. And this is a cool down time, literally, because the lasers need to cool down because they get so hot from firing that much energy at once. To make it commercial, we need to do a repetition rate of around 15 times a second. So that's the first challenge. The second challenge is that we must supply around 500,000 targets per day to be able to produce an output that's viable for our grid. And not only that, we need to have each target cost around 25 cents, which is about 10,000 times cheaper than they currently cost. The third thing that we need to work on is the gain. The best gain we've achieved to date in 2025 was around 4 times, where we got 2 megajoules producing 8.6 megajoules. We can see that this is increasing. So how big would this need to be commercially viable? Well, we need to produce about 150 megajoules out of 2 megajoules. And this paper here says that it needs to be almost 100 times larger for repetition rates of around 1 to 20 hertz. And that comes with a huge range of difficulties associated with plasma stabilities. So why are we funding the National Ignition Facility, given that this seems so difficult to make commercially viable? These are all orders of magnitude changes. Well, if we look at the history of fusion research, we can see that there's a strong correlation with nuclear weapons desires. Here we see a dip in fusion research after the end of the Cold War. And this came as a result of the Comprehensive Nuclear Test Ban Treaty, which prevented any country from doing nuclear tests using actual nuclear bomb explosions. Now, China and the United States have not yet ratified it, which means it's not yet legally binding, but they haven't done any nuclear tests since. Straight after this ban, in America, they produced a new government agency called the Stockpile Stewardship Program. This was started in 1993. And we can still see that today, the predominant focus of the Stockpile Stewardship Program is bombs. Here, their near-term goal is to deliver the B-61 gravity bomb. What else started in 1993, you ask? Well, it was the National Ignition Facility, which has started off funding from the Stockpile Stewardship Program to try and achieve ignition whilst not doing nuclear bomb testing. And this means that they can research nuclear bombs without dropping nuclear bombs. And straight after they achieved ignition in NIF in 2022, they released a bunch of articles which shows that they're not hiding their true goals, which is to improve the safety, reliability and resilience of their nuclear arsenal. The reason that ignition is so crucial for the nuclear arsenal is because most of nuclear bomb testing is simulated. And the problem with simulating it is that you can't confirm it with real data unless you've got that real data. And so achieving ignition allows them to look at very, very hot, high-density conditions that you would see right at the moment that a nuclear bomb explodes, and they can confirm all of the simulations for which they're using to build new nuclear weapons. The National Ignition Facility provides a comprehensive test ban treaty compliant capability to test existing warheads.
So, fusion research today is a diverse landscape that, like every single science, is simplified by the wider media. I mean, what scientific discipline do you know that isn't, oversimplified and reduced and summarized by mainstream media? And this makes sense, it helps people understand it. And they miss over key nuances, of course they do. They're not professional scientists, they're science communicators, or they're just, mainstream media presenters. I mean, sure, it's their job to be accurate, but skimming over a certain level of detail and, potentially being a little enthusiastic about their discoveries isn't the worst thing in the world. So why are we talking about fusion instead of talking about other sciences which are misrepresented by the media? Well, the reason is because fusion has something that sets it apart. So let's set the stakes a little here. You've probably all heard of the Paris Accords. Every country in the world practically pledged to maintain the temperature increase over pre-industrial conditions to about 2 degrees Celsius. And that was over 10 years ago. Obviously, attitudes have since changed, this particular agreement. But let's have a look at what it would look like in a world where we did manage to meet these goals. Well, first of all, natural disasters would become a lot more common. It's very easy to think, okay, 1 degree, 2 degrees warming, what difference is that going to make? But it's not about the fact that we're actually looking at a hotter world. It's about the fact that we're looking at a more unpredictable world. I mean, the climate is driven by a complex series of circulating cells and currents and jet streams and all of these things that can be tipped in the balance if temperatures change very slightly. And as a result of this, disasters scale non-linearly with temperature shifts. I mean, even if the average is barely shifting, a once-in-a-100-year event is going to become a once-in-10-year event. And current infrastructure is simply not designed to cope with this. And as a result, this has led to 50 million more deaths being projected by the WEF in the next 25 years, and that's just from natural disasters. But a more pressing issue could be said to be agriculture. I mean, currently about half the world's households rely on employment either in subsistence farming or selling the products of farming. And at 2 degrees warming, which to remind you is our current goal, almost a third of crop growing regions near the equator will be unsuitable for their current crop growing purpose. And this could rise to half under 3 degrees of warming. I mean, this is a huge proportion of the world's population, people that are barely above the poverty line, that suddenly all at once are going to see their livelihoods being unsustainable. And that's going to inevitably lead to a mass migration crisis. I mean, during the past decade, 70,000 people have been displaced as a direct result of climate change every single day. And in the next 25 years, an additional 216 million people may have to permanently relocate as a result of climate change. I mean, this could be their previous homes or their livelihoods being destroyed, and that's going to mean that basically 3 times the population of the UK are shifting from the equator to somewhere either northward or southward. And, as countries are closing their borders more and more, this is going to lead to conflict, and it's going to lead to the deaths of millions and millions of human beings. So when we look at actually how we're doing in terms of our goals, we can see that current policies, as they stand today, will lead to a catastrophic temperature rise of up to 3.1 degrees Celsius. That's higher than anything. I mean, it's tempting to say that that's slightly worse than 2, but actually it's twice as bad when you look at most metrics. I mean, it's technically still possible to meet the 1.5 degree goal, but only with a global G20-led massive mobilization to cut all greenhouse gas emissions starting last year. Current commitments for 2030 are not even being met, and even if they are met, that would still lead to a catastrophic temperature rise of 2.7 degrees Celsius, roughly. So we're not on target, not even close. I mean, you might think that, we're doing better and better every year and more investment in solar and wind and what have you, but every single year there are more carbon emissions than there were in the previous year. It's not hopeless, but it's certainly not looking good. I mean, if you can see in these models, roughly what we're aiming for are these two, the light blue and the dark blue lines, and we're about here. In the 2.7 range right now. But if we continue our decline, as Donald Trump has recently announced that he doesn't really think climate change is real, if we continue along that trend, we're going to be looking more into the dark red line, which is well over 3 degrees warming, which is not a world that I would like to live in, personally. So, just to summarize, climate change isn't about an apocalypse. There's language about the tipping point and disaster movies about tidal waves that consume the Empire State Building. This isn't necessarily realistic. A coastal city isn't going to drown. It's just going to become uneconomical. And slowly civilization won't collapse, but it will simply no longer be as optimized. Everything will just be a little bit harder than it was before. And some of the world's wealthiest people, probably many of you watching, will barely feel the impact of climate change. That's true. But billions of the world's most vulnerable people will probably die during this process of us shifting to this new baseline. I mean, humanity's never really seen a mass population loss since the last mega eruption. And I think, personally, it would be a tragedy if we allowed this to happen. So this is Alondra Nelson, the Director of White House Office Science and Technology Policy, saying that fusion can help America reach the goal of net zero emissions by 2050, commensurate with the scale that climate change requires. That's a big claim, of course. And she's not entirely wrong. I mean, you'll see a lot of people talking about the fact that nuclear fusion is a huge prospect for climate change and for green energy. I mean, the answer that you hear very often is that it has an abundant fuel supply. There's no chance of a nuclear accident, no Chernobyls, no Fukushimas, nothing like that. And there's very little nuclear waste that gets produced. These are the talking points that you see on the media very often. And not only this, but the energy density of the reaction is huge. I mean, you get essentially huge amounts of free energy for very little fuel, and it's incredibly efficient. And you might think this means that, okay, we're getting more bang for our buck here. But actually, fusion isn't about that. Fusion is more expensive per unit of energy, per watt, than equivalent energies like fission, and especially compared to renewables like solar and onshore wind, which are currently incredibly cheap and only getting cheaper. So wait a second, if fusion isn't the cheapest energy per unit energy, then why are we pursuing it so much? Well, it's actually more complicated than that. The flexibility and the power density is in itself quite valuable to energy grids. The ability to deliver firm power at the flick of a switch and isn't affected by seasons or storage or any of these things that renewables have to worry about. It doesn't actually have to compete with renewables when it comes to grid penetration. If you look at this graph, when we get to like 60-70% of the energy grid being taken up by wind and solar and stuff like that, you see this diminishing return. The actual cost per unit energy, the LCO, which is the levelized cost of electricity, that actually goes up as you go over 70. So the perfect grid, the grid that we really want to save the planet, is something that has around 60-70% renewables and then 30% of really flexible baseload energy that we can turn on and off whenever we like. And that can make up for seasonal losses or, declining wind speed, stuff like that you'd see in renewables. Actually, here are some potential models of what a grid might look like that incorporates fusion. But here you can see that they're predicting that fusion is going to take up a lot of the space in the future that's currently being taken up by fission or by carbon captured gas or coal. So there is a world in which fusion can actually really help us in order to achieve our climate goals, and it's not there to compete with renewables, it's there to actually aid them. And in all these scenarios analysed in the paper that we just looked at, fusion's being made available from 2050 onwards. So the question really is that a realistic goal? But let's get into actually how nuclear fusion works on a more physicsy, scientific level.
Let's go back to basics. Nuclear fusion reactions make energy. You start with two light elements, you push them together, and you get a heavier element. You also probably get some light physical products that come off. And crucially, you get lots of energy. But you actually need really extreme conditions to be able to create this reaction, because every single fusion reaction requires a quantum tunneling event where you push the nuclei of the two atoms very close together, so close in fact that there's a small non-zero chance that they'll just tunnel inside of each other's Coulomb repulsion and therefore fuse to become one heavier nuclei. The problem with this is that the chance of which they'll fuse for all of the relevant temperatures is significantly lower than the chance that they'll just bounce off of each other. We can see on the graph on the left the cross-section, which is essentially the reaction rate, Coulomb scattering, which is the scattering or bouncing off of each other caused by the Coulomb force or the electrostatic force, dominates across all of the temperature range. We can also see from this graph the reaction rate of the fusion reactions, both deuterium-tritium DT and deuterium-deuterium DD fusion, increases as we increase the temperature up to a certain point. And then there's a maximum temperature, around 100 kiloelectron volts, which is in the hundreds of millions of degrees, for which we get maximized deuterium-tritium fusion reactions. Now, what are the problems with achieving this extremely high nuclear fusion reaction temperature? Well, we have to have them in the plasma state because they're so hot that the electrons can't stick to the ions anymore. And in this plasma state, we have very large plasma losses, which is the emission of energy from the plasma just because it's so hot and so plasma-y. These emissions can come in basically two different categories. Either we get sort of kinetic emissions of energy, where products of the reaction leave the reaction depositing energy elsewhere, or we can get deceleration energy, where the deceleration of charged particles in both Bremsstrahlung radiation and synchrotron radiation emits light, because as the charged particle decelerates, its electric field ripples, and those ripples come off with light energy. We found this balancing act where we've got this measurement of Lawson criterion, which is essentially the plasma density times a thing called the confinement time. And these two products against temperature produce this boundary, for which along this boundary you get a point where the losses of energy per second from the plasma is equivalent to the gain of energy per second from the fusion reactions occurring within the plasma. Because if you increase the temperature, you get more fusion, but you also get more plasma losses. And so there's a balancing act here, and that creates this boundary line, the black line here. This black line is the ignition, the same ignition that was achieved in the National Ignition Facility. But what about the energy released by fusion, the plasma losses? Doesn't that heat the cooling plasma back up if we were to feed it back in? Well, we could do this, and people have looked into this, where you take the energy that is emitted by the plasma, and with a certain efficiency ratio, you feed that back in to sustain the fusion reaction. But what they've determined, actually, is that the amount of energy required to feed it back in just to sustain the reaction requires such a high recirculation efficiency of around 50%, or in this other study, 40 to 60% recirculation energy. There will be a major concern for fusion power plants that if they attempt to run under the ignition conditions, that the energy cost from recirculation is so high that the efficiency of the total power plant would be tanked to the extent that they became no longer commercially viable. Essentially, a high Lawson criterion and achieved ignition is a necessary condition for a commercial fusion power plant. So what are the different methods for generating a high Lawson criterion? Because you'd expect a field that has existed for as long as fusion has to have converged on a special idea that is the best of these ideas. So there are many different kinds of fuels that are currently being used. There are many different kinds of confinement that are being used. Be it pulsed operation or continuous operation, be it magneto-inertial, inertial or magnetic, be it deuterium, tritium, proton boron, deuterium, helium-3. There's a huge variety. Let's start by dissecting this graph by looking at the different kinds of confinement. So there are 3 different kinds of confinement that we can do. We can either do magnetic confinement, inertial confinement, or a combination of magnetic and inertial confinement called magneto-inertial confinement. Let's start with magnetic confinement. Magnetic confinement works off this idea of constraining charged particles to magnetic field lines using the Lorentz force, where the combination of electric and magnetic fields means that charged particles will spin around magnetic field lines like planets spinning around the sun. And the idea here is that if you can confine all of your charged particles to move along this sort of racetrack of magnetic field lines, eventually they'll crash into each other like race cars. And we hope that the energy to which they crash into each other is enough that they will fuse together. So let's build a racetrack. Well, we can build a solenoid which has these straight field lines that passes through the middle of them by putting a current through a corkscrew wire. But we don't want a straight line solenoid because then our charged particles will shoot off into the distance and we can't watch them. Just like Formula 1 cars, we then build a circular racetrack, so they travel in circles. And the most geometrically stable version of this is a perfect donut. The problem with the donut idea, though, is that the density of field lines near the centre is higher than that near the edge. And the result of that is the electrons and ions will separate. Due to their charge, they'll drift in opposite directions because they're oppositely charged, and this results in charge separation. And the problem with charge separation is that it generates instabilities within the plasma as a whole, unbalanced forces, and a stable confinement is not possible. Why is a stable confinement a big deal? Well, unstable confinement leads to plasma disruptions. Due to the temperature of the plasma, and therefore the velocity of the charged particles moving within them, if they even touch a physical object, they'll cook it. And that means that future use of the plasma wall is compromised. Current methods for dealing with plasma injection involve the injection of a shattered pellet as shown in this video. And it's a beautiful thing, but what it does essentially is it injects gases that will not fuse into the fusion reaction, increasing the volume of the fusion reaction and cooling it down. This was sent by the UK Atomic Energy Association. So how do we prevent drift and therefore disruptions in the plasma? Well, we want to twist the field lines, and therefore, when the electrons are travelling down in one part of the field, they'll be travelling in the opposite direction up in the other parts of the field, and therefore will sort of even out as they travel around the donut. And this means we get an even density of electrons and ions throughout the entirety of the donut. And there's 2 main ways of twisting the plasma at the moment to be able to achieve this even density of electrons and ions, and therefore a stable plasma. The first one is a stellarator, where you've got these incredibly complex geometries of magnets that twist the actual shape of the plasma as a whole, the bulk. Or you've got a tokamak where you stick a giant magnet inside of the currently toroidal magnetic fields. You stick in what's called a poloidal one, and the sum of the magnetic fields from this poloidal and toroidal magnetic field results in this spiral helix donut shape, which confines the electrons and ions and keeps them evenly distributed. It should be noted for a tokamak, to achieve this twisted magnetic field, they have to run a transformer-like magnet on the inside. This magnet is run through a constantly changing current. And because the current has got to be constantly changing in the same direction, because you can't change it like alternating current back and forth because that would reverse the direction of the magnet and therefore slow down the ions and stop the fusion reaction, you've always got to be running it in one direction. And the problem with running it in one direction is that after a point you'll achieve a maximum possible current. If you're constantly accelerating the current in one direction, there's got to be a top-end speed. And once you achieve that speed, you can't keep accelerating the current, and therefore the magnetic field must stop. Therefore, you've got to cut the current entirely and restart from the bottom again. This results in pulsed running of the tokamak. You cannot continuously run the tokamak because of the way that this inner transformer-like magnet works. So therefore, stellarators would be a good idea, but stellarators are so complicated to create, that geometric magnetic layout is so difficult, that practically all of the funding has gone towards tokamaks. Ever since the 1960s, it was quickly identified as the most promising approach, and remains so today, with the biggest tokamak in the world in ITER, which is the most likely first step towards a commercial fusion reactor in the future. Which brings us on to our second confinement method, inertial confinement fusion. Here's the National Ignition Facility, which we spoke about earlier. You can see the size of the laser housing that's required to go into the fusion reaction, taking up these two giant warehouses. The basic idea here is to use the kinetic energy of the lasers to compress the fuel and heat them up to conditions where they get enough fusion reactions per second that they release energy. Another idea in inertial confinement fusion is by a startup called First Light Fusion, which uses a giant gun to fire a projectile containing the fuel into a wall, and when it hits the wall at 14,500 miles an hour, it should have enough kinetic energy within itself that it gets hot enough in that instantaneous moment that there's a net energy release. Most of inertial confinement fusion runs off these two kinds of ideas, either using a giant kinetic setup or a lot of lasers, basically to heat up the fuel. The third idea is magneto-inertial confinement. This is an image of magneto-inertial confinement fusion running an idea called fast ignition, where they first squeeze the plasma using a magnetic field and then inject a really high-energy laser to push it just over the edge of ignition and get some energy out. It should be noted that this is being done by First Light Fusion, which is the same company as the previous slide who made this gun. Now, why is First Light Fusion doing a completely new thing? Well, it's because funding ran out on the gun idea, and in the last 9 months they've completely switched direction and are hiring new PhD students to work on this new fast ignition idea.
Well, there seems to be an obvious choice. If we look at this graph of triple products, which is basically the reaction rate against temperature, we can see that we get the most effective reaction, the lowest triple product, at the lowest temperature from this blue line, which is DT fusion. So, frankly, why would we pick any other fuel? This is what DT fusion actually looks like. D stands for deuterium, which is an isotope of hydrogen with one neutron added to it. Tritium here is the same thing, but with one extra neutron on top of that. So here you can see it's fusing to create a helium atom, as well as a neutron, as well as the energy that we require from fusion. Now, you hear a lot of people saying that deuterium is readily found in seawater. In fact, 1 gallon can produce as much energy as 300 gallons of gasoline. I mean, that's down to the energy density of fusion, right? But actually, when we look at tritium, which is the other component of DT fusion, we don't see this kind of abundance. Demo, which is the planned reactor after ITER, the first commercial reactor that's going to hit the scene, that's expected to consume about 111.2 kilograms of tritium per year. And currently, the global stockpile of tritium is only 20 kilograms, which is about the size of a medium-sized dog. So there's a bit of a discrepancy here. As you can see, we do not have enough tritium to sustain a commercial reactor. So what's the plan? We have to breed it. What does that look like? So in an average fusion reaction, as I mentioned, we produce neutrons. Now these neutrons are incredibly useful because we can use them to react with an atom of lithium. And through that reaction, we can produce a tritium. Now that tritium can be recycled into the original reaction and then used essentially to create a self-sufficient fuel supply. Every tritium that we create from an oncoming neutron can then use to create more fusion, which creates more neutrons, and the cycle continues. Now, in order for that to work, of course, we need to be getting more tritium than we lose. We need to have a ratio, a tritium breeding ratio, a TBR, of more than 1, right? And in order to achieve that, there's another thing that we have in this blanket, the breeding blanket where we breed the tritium. This extra component is called the neutron multiplier, and the role of this is to receive an oncoming neutron from the original reaction and actually react with it and produce 2 more neutrons, which means that for every neutron we're using from the reaction, instead of having to rely on that making 1 per tritium, we can also have a neutron multiplier in the middle, and that doubles the number of neutrons we get per neutron, which increases the chances that a lithium will turn into a tritium, which can then be recycled. This is all in an effort to get our TBR as high as possible. Now, when we're choosing a neutron multiplier, there's a few things to consider. The grey dots here are the chance of a reaction producing 2 neutrons, and the black and orange dots are when the reaction basically just produces gamma rays. So for the 2 neutron reaction, we want that ratio to be as high as possible. We want a very big difference between the grey and the black and orange dots in order for it to be an appropriate neutron multiplier, which means that it produces very often 2 neutrons per incoming neutron. And the 2 that we can see that are very appropriate, the 2 green bars in this graph, we can see that lines to beryllium and lead. They are the only ones found to be appropriate choices for neutron multipliers. Now, as you can see, we also need to consider the density of lithium atoms, because if we want to try and maximize the chances that a neutron's going to hit a lithium, we need to have a sort of lattice that has many, many lithium atoms per unit of area. Now, the lithium also needs to be optimized in its own way. So there are two isotopes of lithium that exist naturally in the world. These are lithium-6 and lithium-7. Now, lithium-7 is by far the most abundant. Almost 93% of natural lithium comes in the form of lithium-7, which means it has one extra neutron, right? It's heavier. But lithium-6 is actually the one that we want in order to have a breeding blanket, right? Because lithium-6 can react with lower energy neutrons. From this graph here of incident energy against neutron cross-section, we can see that almost for the entire range of incident energy of neutrons, lithium-6 is actually the only element that's reacting with the neutrons. So obviously, we want as much lithium-6 as possible in order to mean that over a wider range of neutron energies, we can have effective breeding. And because lithium-6 is so rare, we have to enrich the lithium in order to basically remove as much lithium-7 as possible in order to get that tritium breeding ratio as high as we can. These are a couple of the practical designs of breeding blankets. The HCPB stands for helium-cooled pebble bed, and the WCLL stands for water-cooled lithium lead. These are both different designs that use different substrates for lithium. They use different ways to cool the reactor. They're basically competing right now to be the design that's going to be used in the demo reactor. The ITER reactor is not actually going to have a functioning breeding blanket, but it's the demo reactor that's going to ideally have this first proper breeding blanket in place. And that's going to be taking one of these two designs. They're both looking pretty good. A lot of papers are backing one or the other. By the way, just to draw your attention to the scales here, that's 35 meters. I mean, 35 meters is bigger than a blue whale. So, these are not small scale engineering projects, right? These are very, very large. Let's have a look at the WCLL. This is what it looks like in a sort of basic diagram. You can see the neutron source, that's where the plasma is, and that's emitting a lot of neutrons into the small black line, which is the first wall. That's the first line of defense against the oncoming neutrons. And then the green, that's the liquid alloy. So that's liquid metal, lead and lithium alloy of metal, which is 400 meters cubed in total. And that's swirling and swirling around in this layer around the reactor itself in these green stripes, as you can see. The water, the blue stripes, that's used to sort of control the temperature of the reaction. And then you can see the red, that's just structural material, that's just steel. RAFM, reduced activation steel. We'll talk about that a bit later. So here is the actual design that details how the tritium gets from the alloy itself, where it's been bred, back into the plasma, where it can be used as fuel, because that's an important part of the recycling process, right? So this is the PAV, which is going to be used in the WCLL. It's a very clever design. Basically, it uses this vacuum permeator concept, which this is one single unit of it, but actually there'll be many, many of these units all stacked in this big sort of lung, basically. And the idea is that it passes this alloy, this liquid metal alloy, through this tube, and the membrane itself is made of palladium silver. Palladium silver alloy acts as a permeable membrane for the tritium, because the tritium can pass through this palladium silver alloy into the vacuum surrounding it, but the liquid lead lithium can't. So the lead lithium acts like sort of blood, and the tritium acts like oxygen. You can think about it like that. And you can see the vacuum is pulling the tritium through this membrane, and then the tritium can be filtered for impurities like helium and hydrogen, and then re-injected into the reactor. So that's how the tritium is actually going to be recycled in a practical way, if we go with the WCLL, that is. And here is a summary of the progress that we've made so far. I mean, you can see that in 2022, they've been doing a lot of simulations which suggest that actually we can achieve tritium breeding ratios over 1. I mean, you can see on the TBR, which is on the y-axis, we're talking 1.1, 1.13. We're actually getting quite high. And baseline 2022 was a simulation that detailed the highest tritium breeding ratio, roughly 1.127. But actually, 1.165, which is baseline 2024, exceeded even that. You can see in the graph on the right that it's the blue line, the one that's enriched with 90% lithium-6, that actually achieves the highest tritium breeding ratio. And that's what they used to get baseline 2022. And that seems pretty good. I mean, we're looking for a tritium breeding ratio over 1, and it looks like we've achieved it. But actually, the reality of the situation is that all of these are simply computer simulations. But at the end of the day, we've never built a breeding blanket before. We've never even tried. So all of this is still theoretical. And when you build something, when you take something from theory into practice, very often problems come up. Problems that you didn't foresee, potentially. For example, here are a lot of ways which tritium breeding ratio can take a hit as a result of quite small engineering decisions. So in this thing, you can see that the 2.8 centimeters is the idea for their tungsten first wall. And in the graph underneath that, you can see that with 2.8 centimeters, you'd actually take a huge hit in the tritium breeding ratio. Not only that, but if you just add another diverter, for example. Now, diverters are like an exhaust system, kind of, that sort of suck all the impurities out of the plasma. If you add 2 diverters as opposed to 1, then tritium breeding ratio also takes a hit because the neutrons that pass through the diverter aren't actually making it to the breeding blanket. Not only this, but this is a saturation curve, basically, which represents how the total breeder thickness, so the thickness of the blanket itself, actually demonstrates diminishing returns with the breeding ratio. The thicker your breeding blanket is, the more that's going to be soaked up in the first few layers of the blanket, the areas closest to the neutron source itself, and the further you get from that neutron source, they'll be receiving less and less neutrons. So it's not like you can just build a bigger blanket if you want more tritium. It's not quite that simple. Here we can also see something which barely anyone takes into account in their models. This is tritium permeation. Now, tritium is a tiny, tiny atom. It's basically the size of hydrogen with a couple of extra neutrons, and that's really, really small. I mean, it will kind of soak into all your reactor components like water into tissue paper. You know, it's very, very tiny, and it gets stuck into things like the vessel wall, the structural steel, the breeding blanket itself, the diverter. All of these things soak up tritium over time, and as a result, that tritium can't be used as fuel, which means that this is another way in which the tritium breeding ratio can decrease. Now, some people think this is a huge problem. There's a suggestion that tritium trapping may significantly influence the first fusion power plant's ability to be self-sufficient, and that none of the models today are remotely accounting for this. However, some people think that, the importance of tritium retention is a little overestimated, and actually you can still achieve self-sufficiency, even if a little bit of tritium gets stuck along the way. But this is kind of my point. This is an area of scientific debate. We do not know right now which of these theories about tritium trapping and tritium retention being an influential factor, we don't know which is correct because we've never built a breeding blanket. These are all simulations. So as much as people are saying, yeah, we've achieved tritium breeding ratio over 1, in fact, we really haven't. The majority of problems that will actually come up in a practical design for a breeding blanket just haven't had to be reconciliated. We haven't had to deal with them yet because it's all theoretical. And the first time we're going to be building one of those is in demo, so that's still quite a long way off, and the science isn't actually where it should be at the moment. Oh, and by the way, if you ever wondered what might happen if you take 400 meters cubed of liquid lead-lithium alloy and surround it with layers of cooling water, well, I mean, if you think back to chemistry class, it's not exactly great when you mix large amounts of liquid lithium and water together. You tend to have a pretty extreme exothermic reaction. So, they tend to like saying that fusion reactors can't melt down or something like that, or there's no chance of a disaster. But we need to remember that we're still working with incredibly reactive materials, even in the most basic fusion design. So yeah, breeding blankets are definitely a long way off.
Now it's time to talk about that neutron that was emitted from the deuterium-tritium reaction earlier. The neutron that's emitted in this reaction carries 80% of the total reaction energy away from this reaction, and it is also important to say that in a deuterium-tritium reaction, they emit the most neutrons, and those neutrons have the highest amount of energy. Now, fission reactions also produce neutrons. Here is a comparison of the neutron energies and the neutron quantities produced from a fission plant and the possible fusion demo plant, and these are at the same power outputs for these two plants. There's very few cases of neutron irradiation deaths, but one of the most famous ones is the Demon Core incident, where testing for a nuclear fission bomb in the 1950s, a scientist was varying the criticality of a plutonium core using a screwdriver. When he slipped and the screwdriver fell out, the core went critical, emitting large quantities of radiation, including neutron radiation. Here's an image of his burned hand shortly afterwards, because a second after it went critical, he was able to slap the container, the moderator, and make it go subcritical again. The reaction only lasted a second, but it turned the room around it blue and gave him enough radiation, around 10 to 20 sieverts, that he died within a week. The reason that the room went blue is because of Cherenkov radiation, which is where charged particles travel faster than the speed of light through that medium. So these will be caused by the electrons that came off the critical core. And it's sort of like a sonic boom, but for light. So back to that graph of the comparison between fission neutron energies and fusion neutron energies. I believe this graph hides quite a significant detail. Due to the logarithmic axes, if we smooth them out and make them linear axes, we see at the top end of the graph a much higher emission of much higher energy neutrons in the fusion power plant compared to the fission power plant. Here's a comparison of the mean, median, and mode energies of fusion and fission reaction emissions. We see that across all of them, fusion emits much, much more powerful neutrons. And the distributions show this as well. We see that there's a slanted graph for fission emissions, with a peak around 0.8 MeV and an average of 2 megaelectron volts. Whereas for fusion, we see the peak is around 14 MeV and it's not slanted, so the mean, mode, and median are all around 14 MeV. So we can see that nuclear fusion releases much, much more higher energy neutrons than nuclear fission. So why is this energy so scary? Well, neutrons are neutral. The key's in the name. And because they're neutral, they can't be constrained by the electromagnetic field, and therefore they pass through as if nothing's happening at around 130,000 Mach and smash into the outer container of your fusion reactor, and indeed the rest of your fusion plant. They move like bullets, and like bullets, they cause problems in the structure of the surrounding area. They can either transmute atoms, where they turn them into other atoms, or they can just scatter, where they move them from their original location by depositing kinetic energy. This can wreak havoc in a lattice, causing dislocations, crowdings, emissions of gases within the lattice, and transmutations of atoms. That's not a biggie if there aren't that many neutrons. So how many neutrons are there? Here's a comparison of the amount of neutrons and the neutron flux seen by different areas of the reactor. The neutron flux in the diverter here is said to be 5.2 times 10 to the 16 neutrons per meter squared per second, which sounds like a lot. And over time, through the full power year, which is the FPY description we see there, it'll achieve 1.6 times 10 to the 24 neutrons over a full power year of usage. Thought it'd be interesting and fun to do a unit conversion, just to see how many neutrons will be passing through per angstrom squared instead of per meter squared. An angstrom is roughly the diameter of an atom. So this is how many will pass through a sort of local atom area. And if you work out the number of neutrons passing through each angstrom squared, you'll see a neutron roughly every 2,000 seconds. 2,000 seconds is about 32 minutes, which makes it a similar Poisson distribution as trains going from London to Edinburgh. The first wall is the first wall that will see neutron fluxes. It's the inner lining of the vacuum vessel for a demo reactor. And the primary candidate at the moment for a first wall is tungsten, as the material that will see the largest quantities of neutron flux, and indeed tungsten is planned to be used in the diverter. Previously, beryllium was considered, but beryllium has huge issues with tritium embrittlement, and it has issues with being sheared off in sputtering, and it doesn't do very well with neutron irradiation. So recently, ITER has planned to switch from beryllium in its inner wall to tungsten. Tungsten has its own issues because tungsten is very heavy compared to beryllium, and therefore impurities of tungsten that go into the vacuum in the vacuum vessel and enter the plasma would be so heavy that they would slow down the local plasma particles and cause them to drop below ignition at concentrations as low as 20 parts per million. So you'd need to have the tungsten all staying on the wall, which is not easy. And the second issue with tungsten is for any sort of nation to be running any sort of demo power plants at the moment to be commercially viable. The tungsten supply chains and tungsten mining in the world is not large enough to sustain the quantity of tungsten that would be consumed by these demo power plants. There would need to be a complete overhaul of the tungsten mining industry, which again is difficult to do by 2050. Anyway, reaction rates between atoms in each angstrom squared and neutrons is an important thing to consider, because actually they're very low, and they're measured in a unit called barns. For tungsten and 14 megaelectron-volt neutrons, they have a cross-section or a reaction rate of 5.4 barns. A barn is a unit that was described because when they measured it, it was much larger than what they expected the actual cross-section of a nuclei to be, which was 1 times 10 to the minus 30 meters squared, because a nucleus has a diameter of roughly 10 to the minus 15 meters. And so when the scientists discovered this, due to quantum interactions, they exclaimed that it was as big as a barn. So 5.4 barns, and we've got 1 neutron passing through every 30 minutes. How many primary knock-on atoms are we creating? Well, every year, 1 in every 1,000 atoms, or 8.84 times 10 to the minus 4 by my calculations, get hit directly by a neutron. So that's 1 in every 1,000 atoms become a primary knock-on atom. 1 in every 1,000 doesn't sound too bad until you realize that a primary knock-on atom destroys the local lattice. Here we can see a simulation of a 10 kiloelectron-volt gold primary knock-on atom hitting a gold lattice. These atoms get so hot in the surrounding area that they're called liquid atoms, and that's because their kinetic energy is high enough that they pass into the threshold of what can be classified as a liquid. The high-energy neutrons produced by the deuterium-tritium fusion plasma give rise to primary recoils in tungsten with average energies of around 150 kiloelectron volts. So that's 15 times higher than this simulation. and this results in lattice cascades. Here we can see tungsten and iron on the left and just tungsten on the right. In these cascades, the earlier time periods are drawn in red and the later time periods are drawn in blue. It's an incredibly destructive process when a neutron interacts. At its peak, the tungsten atom from a deuterium-tritium neutron is expected to produce a liquid area of around 30,000 atoms. So how many individual atoms are affected per year? All of them. About 9 times each, according to our calculations. But why listen to our calculations when it's been simulated for demo power plants in multiple different materials? We can see here we've got double digits displacements per atom per full power year. Here we see another simulation at different locations within the D-shaped cross-section of a tokamak. And again, for different locations inside this D cross-section, not including the diverter, we see very, very high displacements per atom per full power year. Here it has been measured for breeding blankets. We can see the orange line is the water-cooled lead-lithium blanket that is expected to be used in the demo power plant. So what's wrong with displacements per atom? Well, it creates voids in the lattice, turning it into sort of Emmentaler cheese, which decreases the strength of the materials and causes them to have to be replaced over time. Here we can see voids in tungsten in the bottom right in figure D, with 1.5 displacements per atom at a temperature of 750 degrees C. In the real reactor, we will be using an alloy of tungsten, and so expect to see less displacements per atom. Note that the temperature increase will result in more voids, as the particles are freer to move.
So aside from the neutron simply battering a nucleus apart and splitting it into different pieces, we also have to worry about an oncoming neutron fundamentally changing the nucleus that it's hitting. I mean, this can occur through transmutations, which is when a neutron adds or in any way changes the nucleus to turn it into a heavier or radioactive isotope or even a different element. Here is a graph of potential radioactive transmutations that can occur just from tungsten. As you can see, tungsten, which is W on the periodic table, can turn into things like rhenium or osmium from oncoming neutron transmutations. So you often hear media say stuff like there's no long-lived nuclear waste that's produced from nuclear fusion. And technically this is true. They are able to say that because nuclear waste is divided into 3 categories, right? You have, low-level, intermediate, and high-level waste. High-level waste is the long-lived stuff. That's the stuff that lasts for hundreds of millions of years. And fusion doesn't produce that kind of thing. It's nowhere near as bad as in fission. But nowhere near as bad as fission still means tens or hundreds of years, potentially, of dangerous waste that cannot be tampered with and could kill a person in mere seconds. This stuff still needs to be disposed of and managed in a similar way to high-level waste, certainly in the short term. But it's very important to remember the fact that, yes, fusion doesn't produce as long-lived nuclear waste, but by volume, it produces far, far more than fission. With fission, it's like a toaster, right? You can remove the toast, which is the cooling rods. That stuff you can store safely and make sure no human can interact with it. But when it comes to fusion, the toaster itself becomes the radioactive waste. The neutrons irradiate and transmutate the materials that make up the reactor walls itself. And this can produce, by weight, up to 10,000 tons of solid radioactive waste, dangerous waste, from in-vessel components alone. Now that's equivalent roughly to, that's equivalent to 44 Statues of Liberty worth of dangerous, heavy, radioactive waste that has to be stored and maintained away from any human being for at least decades, if not centuries. One of the reasons it's so dangerous is I mentioned tritium and tritium permeation earlier. Well, this tritium is actually a beta emitter itself. It's actually so deadly that up to 1 milligram of tritium ingested could be a lethal dose. And this tritium is leaching into the materials itself, and over time, as it's kept in its storage facility, the tritium will slowly diffuse back out. Now, tritium is not something that we're very good at storing. As I mentioned, it's so easy for tritium to slip through cracks and slip through lattices because it's so tiny, it's such a tiny atom. So tritium is not something we're very good at storing, and current repositories are not designed for large amounts of tritium because we never had to store it before. So tritium permeation is a huge worry in terms of storing nuclear waste from fusion in the future. Not to mention that beryllium, aside from being incredibly toxic itself, contains trace levels of uranium. In fact, if all of the 300 to 400 tons of beryllium in the blanket contained the expected amount of uranium impurities, there would be in total potentially 40 kilograms of uranium in the average breeding blanket. And all of this is liable to be turned into transuranic isotopes, which are incredibly radioactive. And that's the kind of thing that happens in nuclear fission. That's the kind of stuff that you get really worried about. In this picture here, you can see all of the white swirls. That's a uranium and beryllium matrix. So yeah, we have to remove as much uranium as we can from any beryllium that we're going to use as a neutron multiplier. Also, not even that, but the steel itself, the very steel itself contains, things like iron and other metals, and all of that can potentially be transmutated into higher elements like nickel or cobalt, and these things can actually be very dangerous radioactive isotopes themselves. In order to design steel, which is, we mentioned RAFM, that's reduced activation, and that's what the reduced activation part means. You're trying to reduce the, radioactive activation, the transmutations that are possible in the steel from impurities. And you need to really, really minimize the number of impurities in your steel. Normal steel just won't cut it. It's special, purified steel so that you can absolutely be sure that you're barely getting any transmutations during the average lifespan of the reactor. But you can see, even on this graph, even with the most efficiently designed, most pure steel that we can come up with, we're barely making it into the low-level waste class. And some steels that are being considered are actually well into the high-level waste category. Now, of course, the lead-lithium breeding blanket's also an issue. Lead and lithium in the alloy can actually turn into things like mercury, and after only a few days of operation, this level of mercury, the radiological limit that can be safe for handling, can be exceeded. And this polonium-210 that can be created through potential transmutations, that can be 250,000 times more potent, more deadly than cyanide. So this is a huge concern.
So what does this all mean? This is a graph showing the radioactivity of all the different components in a fusion reactor after the shutdown, which is after the total lifespan of the fusion reactor. So it's been running for X number of full power years. Now we've gotten all the energy that we wanted to get out of it, and we've taken it out. Now, the first thing to note on this graph is the hands-on limit, the conservative RH limit, and the advanced RH limit, which is on the side. RH stands for remote handling. Remote handling is a specialized type of robot which is designed to be resistant to radioactivity. And the reason it's conservative and advanced is because they don't have an exact level for what part of the robot will be able to survive what kind of radiation for how long. So we're looking at somewhere in between the two of these. The first wall is clearly the most radioactive part, being it starts around 100,000 sieverts per hour, and after a year is around 10,000 sieverts per hour. This is just about within the advanced remote handling limit, and so they'd be able to use a robot to touch the first wall a year after the shutdown. Let's look at the units sievert per hour. Remember that guy who slapped the demon core after it turned the room blue? He received 10 to 20 sieverts in less than a second. At around 10,000 sieverts per hour, in about 3 seconds, you would receive 10 to 20 sieverts. Which means that you can't be near the first wall component, which is the inside of this building-sized donut. Even after a year, being near it will kill you in about 3 seconds. These are very radioactive. Note that they are still radioactive above the hands-on limit, many times above the hands-on limit, even after 100 years after being removed, and therefore all of these will need to be stored in specialized facilities for at least a century. This can be incredibly expensive. Recycling materials is also considered, but this is also incredibly expensive. All of the current radioactive waste facilities are not built to deal with tritium yet. This would require a completely new design, which again adds to the total cost of nuclear fusion energy being commercially viable.
So yeah, to conclude that section, sure, fusion may be able to avoid large amounts of high-level waste in the way that fission can't, but the expected quantities of fusion-derived intermediate and low-level waste are huge.
Another issue with the neutron irradiation we see in the walls of the reactor is the production of gases in the materials of these walls. This happens because when an atom transmutes in the wall, it often knocks off parts of the nuclei which come off as light, protons, neutrons, or like helium atoms or alpha particles. These will then absorb electrons from the surrounding area and become gases. These gases then sit in the material. So this is a graph of the distance from the plasma-facing surface into the wall, and it's the helium concentration after 3 full power years of usage. And you can see that basically helium has saturated in all of the layers all the way back to the back. As you can see in this image here, we see these helium bubbles forming in the tungsten matrix at the first wall. This occurs because helium is incredibly insoluble at low temperatures. So when under running conditions, the helium will build up through emissions caused by transmuted atoms who are hit by neutrons. And then as it cools down, the helium will group together in the lattice, forming these bubbles. And these bubbles will try and come out of solution and will travel towards grain boundaries in the metal. And this leads to local higher concentrations, which decreases the structural integrity of the material as a whole. And we can see on the right-hand side, there are two images of a tungsten surface, which has been hit with a center punch. And in the second image, you can see that it's got a lot less structural integrity and is moving a lot more like Play-Doh than tungsten. Another thing that can happen is that the plasma in the disruptions that we talked about earlier can smash into the side of the vacuum vessel wall. And when they do that, they impart a lot of kinetic energy, which can strip the inside of the first wall. In this high energy process, you can get chemical reactions where the first wall reacts chemically with the material in the plasma. You can get physical reactions where it just strips the inside of the wall in a process called sputtering. You can also get parts of the plasma moving into the wall, which is where you get tritiation, where tritium implants into the wall. And the problem with removing layers in the wall is that you create this structure called fuzz. Fuzz is a structure that occurs when tungsten atoms are removed from the lattice during sputtering, and it's bad for the structural integrity of the lattice. Here we can see some images of a tungsten surface that has been hit with varying levels of helium plasma, similar to the conditions we might see in the deuterium-tritium plasma hitting the wall, that kind of situation. And you can see that the tungsten has sort of degraded over time. So as you can see, there are many different things that affect the structural integrity of the wall and the blanket and the rest of the reactor plant as a whole, due to neutron irradiation, gas implantation, transmutations, and sputtering. So, at what point would we say that these components are no longer safe to use? Well, for the diverter, which is a very heavy component made of tungsten at the bottom of the reaction, it has a lifetime of 2 full power years. Here's another source that says that it requires a replacement every 2 years. But this source also says that the blanket would need to be replaced every other time that the diverter is replaced. Now, this replacement process isn't quick. For example, in this study, they said, assuming a 1-month cooling down period before the remote handling operations can even begin, which means they're so radioactive that you have to wait for them to cool down and stop being as radioactive before you can even get the robots involved, they're that radioactive. And then a 1-month period to condition and pump down before startup, which is after you've removed it and starting it up again. This estimate says that in order to meet a 75% availability target, which is required for commercialization, 4 remote handling systems will be required to handle this radioactive material. And this is just to achieve a 75% availability period, which means for every 2 years of operation, you would need 10 months of cooling or pump down periods just to replace components that are breaking down. And we're expecting this thing to run for 30 years. In short, neutrons. A new foe has appeared. This foe is the field reverse configuration magneto-inertial fusion startup called Helion. Helion is apparently breaking ground, aren't we all, on what could be the world's first fusion plant.
Helion's mission is to build and deploy low-cost electricity for the whole world. We know the rest of the universe is powered on fusion, and I believe that we can do it too.
We already have a machine that runs every day that does fusion. It does fusion in the fuels that we intend to use and at the performance we predict.
Our 6th generation system, we call that Trenta, is operating, doing fusion reactions right now. Trenta got to full scale, showed we can do fusion, and then showed we can recover electricity out of that system. Right next to our manufacturing facility where we're at right now, we're building our 7th generation system that'll be steady operating and demonstrate net electricity for the first time. We call that one Polaris.
With Polaris, we need to increase the scale slightly. We need to increase the amount of energy that we're squeezing that plasma with, and that will increase the fusion output of that plasma.
Our goal is to get that online in the next 3 years and get that working at full power. Fusion is hard, and we have a lot of work left to do to get from where we are to powering your home. There's a lot of work to do, and we need help doing it.
Helion's technology does work, and we're taking the next step to turn that into a commercial product.
We're building the full-scale fusion system and doing this in a way that makes commercial sense. Our goal is to get this out to humanity as soon as possible.
Our mission is to create an energy source that is clean, reliable, and abundant.
Save the world.
And to save the world at the same time.
So wait, a lot of things were said there. Basically, the idea is they're doing this really interesting dumbbell shake weight type of fusion plant. It basically avoids all the issues of the tokamak design. It's literally called aneutronic fusion, which means that it's got no more neutrons, and therefore no more material degradation stuff, we think. And not only that, look at this point 4, electricity recapture. We're not boiling water anymore. We're reabsorbing the energy in the magnetic coils around the fusion reaction itself, because as we fuse, the plasma expands, and because it's an expanding charged mass, we can confine it using magnetic fields, and because we've got this sort of pushing force and pulling force going both ways, we can extract some of that energy as electricity. It's called direct recapture, and it's probably more efficient than boiling water. And people love it. Look at all these YouTube comments. Look at this guy called username9774 saying, "Great to see something actually realistic and close. And isn't it great?" Well, is it realistic? Well, there's some interesting things when we look at the science. For the temperatures they're reporting of about 200 million degrees, which they predict and haven't achieved yet, they've achieved 150 million degrees recently, but they're expecting to produce 200 million degrees, and that's their final output for their commercial fusion power plant. If you look at the reaction rate curve against temperature, at 200 million degrees, the fuel that they're using, deuterium helium-3, has 1,000 times less fusion reactions happening per second. This is a big deal, because per fusion reaction, it releases about the same amount of energy as a DT reaction, and yet it's happening 1,000 times less. Not only that, because of the larger charges involved in deuterium helium-3, because a helium nucleus is 2+ and not 1+, you've got much larger bremsstrahlung losses, which is caused by the deceleration of charged particles. And because you've got more charge decelerating, you've got a greater ripple in the electric field, and therefore you've got more emitted bremsstrahlung light, and that means a greater energy loss. So at what point does this bremsstrahlung energy loss, this plasma loss, balance out with the energy emitted by the fusion reactions for deuterium helium-3? Well, again, looking at the science and looking at the papers, we see that the ignition temperature would be about 30 kiloelectronvolts. But hey, their long-term goal is 200 million degrees, which is 19.2 kiloelectronvolts.
So how are Helion going to ignite? Well, the ugly truth is that Helion actually have no intention of igniting their fusion reaction. So you might wonder how they can claim to get net energy from their reactor if it's not going to ignite. Well, actually, because they claim they have such a high beta, and this is a result of their direct recapture system, where, as the plasma pushes back out, they recapture that energy and apply it straight back in. This basically means that where most fusion systems operate at a beta at about 10%, and that's the ratio of the plasma to the magnetic pressure, whereas Helion claims to be approaching a ratio of almost 100%, well over 95%. So this basically means they have to run an effectively lossless system. They're relying on the fact that they're achieving almost 100% efficiency, which means they can afford to only reclaim a tiny bit of extra energy, go from 95% to 105%. And the fusion itself gives it just that little bit of a kick. And every single time they run this pulsed operation, and they're pulsing at about 10 times a second and hoping that each time they can sort of squeeze a little bit more energy out and just sort of siphon that off into their electrical system. Now, in theory, this could work, but because they have absolutely no transparency about their science, they don't publish papers, they don't really talk about the results of their simulations and of their trials, we really don't know how close to this actual beta value that they currently are. And the main reason people are so skeptical about Helion is, the 100% beta figure is very, very difficult to believe. And due to their fuel choice, they really have to use much, much higher temperatures than they otherwise would. Although, to be fair, it is a significant advantage not to be emitting neutrons. You remember the fire triangle, right? The durability side of things is really helped out by the fact that you're not producing these neutral particles. And you can see here, this is the reaction itself. There's deuterium and helium-3 combining to make a proton and an alpha particle, which is the helium-4 atom itself, and some energy as well. Now, of course, if you have D and D swimming around together, there's no reason that they shouldn't react with each other and produce a tritium, which is the T here, and a proton. And that also produces energy, so that's not the worst thing in the world. But also that same reaction, that DD fusion reaction, can produce a helium-3 atom and a neutron, which, kind of defeats the point, because the whole point of neutronic fusion is to not produce any neutrons, and actually you're still going to be producing some neutrons. Not to mention the fact that if you're producing tritium as well, then you can just go straight back into DT fusion, because there's deuterium and tritium floating around. And because DT has actually got a higher reaction rate at a certain temperature than DH3 or DD, then in this system you'll actually be having a lot of DT fusion reactions, because the reaction rate is so high. So you're actually going to be producing a lot of neutrons, not just a little bit. And that's something they actually need to consider, which they haven't really been considering. They're sort of quite blasé about neutrons, to be honest, which I think is a mistake. And anyway, I mean, this whole thing is supposed to solve the problem of tritium breeding, which is, a good thing, because that's a significant challenge. But helium-3 isn't any more common than tritium is. I mean, we barely have any on Earth. There's a huge scarcity of it. And where it is present, it's only from the decay of tritium, basically, in natural gas wells. So actually, one of the main methods that's been proposed to get enough helium-3 to actually do helium fusion is some samples of lunar soil that they collected from the moon. Has a huge amount of helium-3. So Sam Altman, who gave like 500 million of his own money to this project, has actually suggested that there is a market in potentially mining helium-3 on the moon, which obviously will be very expensive, but will pay back because of the astronomical usefulness of helium-3 in nuclear fusion, according to him. And, you might think that sounds incredibly cost inefficient and quite difficult, but thank God that there's actually a startup announced recently which is claiming to be advancing helium-3 mining technology on the moon with their new prototype. So that's exciting, isn't it? So yeah, our general point here is that startups like to make a lot of big claims. But, let's look at some of those claims that Helion makes. I mean, Helion, actually, if you go on its website today, you can see they say that they're going to be producing electricity for the first commercial power plant that's going to provide energy straight to Microsoft, and that's going to happen in 2028, which, I mean, I don't know when you're watching this video, but at the time of recording, that's only 2 years away, so pretty exciting stuff. Let's have a look at some of the other amazing claims that Helion has made over the years. I think it was in 2014 that they confidently claimed that net fusion was only 3 years away. 2019, it was only 24 months away. And, 2016, it was only 6 years away. 2018, it was only 3 years away. So, yeah, I think there's a bit of a pattern emerging here when it comes to Helion's scientific honesty.
Here is a model called the STAM model. This models the introduction of new science into the marketplace. This highlights the expected stages of commercializing a science product. We can see on the graph that there is ample opportunity to fall behind along the way and even fail. So where does fusion fit into this model? Let's take ITER, the most heavily funded fusion power plant in the world. I believe its subsequent models, such as DEMO and the first-of-a-kind plant, will be the most likely candidates for successful commercialization of fusion power in the future. They believe that ITER is at the science to technology stage, and subsequently the DEMO and first-of-a-kind plant will occur after 40 years. The first-of-a-kind plant being the first normalized, marketable, commercialable fusion power plant in the world. So that's 40 years, but Pietro Barabashi, the current director of ITER, has said that they've had to delay their plans for deuterium-tritium fuel switch-on until 2039. This is 4 years later than the 2035 date that was planned in 2016. If we look at the maths here, we see that 2039 plus 40 is 2079. That's too late for climate change. But what about those private sector fusion power plants? They say they can work a lot faster than ITER. Well, they work on a different system, where they promise fusion rapidly on existing technology. They propose to do it on a much smaller scale and do it iteratively on this smaller scale. They rely on funding, and these investors post goals they need the company to achieve to get more funding. To secure this funding in the increasingly competitive market, they promise fusion on a much faster timescale than ITER. ITER is publicly funded. ITER must therefore disclose all research and all setbacks honestly. Due to the value of intellectual property to startups, these setbacks are often not revealed. This is also to aid their image to their investors. So who's going to win first, ITER or startups? Here is a table from the European Commission Directorate General. This table shows the next device completion dates. This is a proposed device for demonstrating that commercial fusion is possible. The colours indicate how sure they are that the date will slip back from the proposed date. Green is the most reliable and red is the least. ITER is at the top row with the proposed start date of 2039 for deuterium-tritium fusion. All of the other publicly funded reactors are white, as there have been no new proposals for devices to prove commercial viability. The most striking thing about this table is that all privately funded fusion power plants say that they will roll out a working design 10 years before publicly funded fusion. This gets even worse when we look at the actual first commercially viable plants. These are now the demo-level designs for ITER. Privately funded fusion is again years ahead of publicly funded fusion. The only difference is that the European Commission Director General is much less certain about whether these dates will be achieved, as they are a longer extrapolation of the data. So what does the director of ITER say? Well, in a conference that was held after ITER declared that they're going to switch their first wall from beryllium to tungsten, he was asked, is ITER still relevant in the context of immediate pressure of climate change and the emergence of fusion startups? His answer, fusion cannot arrive in time to solve the problems our planet faces today, and investment in other technologies, known and unknown, is absolutely needed. He was also asked if ITER could compete with startups announcing shorter timescales for fusion deployment. To this, he said, he could not comment on the timescales of other projects and only be transparent about his own. So who can comment? Here's a professor of physics at the Max Planck Institute of Physics saying that due to tritium breeding testing being done first at ITER, any reactor promising 10 years is unbelievable to him. He says that as tritium breeding is both an essential component and also an extremely difficult component to get right, saying that they're going to achieve it before someone else is doing the science without doing the science is unbelievable. 89% of the companies who responded to a survey by the Fusion Industry Association in 2024 anticipated that fusion will provide electricity to the grid by the end of the 2030s, and 70% of those companies said that that milestone will happen by the end of 2035. I hope you're as skeptical about this as I am.
Thank you for listening to our video about fusion. Yeah, we just wanted to communicate some of the things that we've discovered after just a few weeks of researching it and really diving deep into the topic.
Yeah.
Thanks for getting this far.
Thanks for getting this far. Don't forget to follow us on the Substandard Model podcast. It's on Spotify, it's on Apple Music, it's on whatever. You can scan that. I think it's a broken QR code now, but just type us in. You'll find us.